So, good morning. Welcome to Krishna's classroom. We continue with our consideration of the Lebesgue integral for measurable non-negative functions. So, this is an improvement from the previous part. There we had assumed that the functions that we considered were not only measurable but bounded, and also they were defined on sets of finite. So we got rid of two conditions. One, boundedness. The other one is it is defined on sets of finite measure. However, we have put a condition that these functions are non-negative functions. Earlier we didn't have that restriction. I have already discussed the reason for considering only non-negative functions at this stage, and maybe we'll get chance when we extend this further to measurable functions on any measurable subset of R. So that in that situation we will say what exactly we want, but for the time being we keep this non-negative. So please note that these are non-negative features. We have already used the strategy or given the strategy while defining the integral, and we were approximating these functions from below by bounded measurable functions on sets of finite measure, okay, which we have discussed in detail, or which we already know what Lebesgue integral is. So our strategy is to look at the entire class of bounded measurable functions on intervals of finite measure which lie below the functions that we are at the moment looking at, and all these functions are, and we need consider only the non-negative functions of that class. Now for which we can talk about the integral comfortably, because they are bounded functions and their domains are sets with finite measure. Now look at the supremum of the entire numbers that are generated by taking the integrals of this. You see that this set of numbers which emerge as the integral of these approximating functions may be bounded or may not be, but they are all non-negative. Okay, right? Therefore, there are two possibilities. The supremum would exist in the sense that if they form a bounded set, then the supremum is finite. If it is not a bounded set, then the supremum is going to be 2. Okay. This second scenario never appeared in the previous case because always the integrals that we defined were finite. Okay. So that is the definition. So we had just to recall the definition that we had made. The definition was the following. we had defined integral of f over e was defined as supremum of integral of h where h is bounded measurable on E with finite support. That means see that H has is defined on some subset of E. Maybe the whole thing is E if E itself has finite measure. Otherwise, on some subset of E such that H is 0 outside this subset. This is what you mean by the function H is bounded measurable on E with finite support. So that you see that because it has a finite support, you see that the integral is different. It's finite. So this was the definition that we had. Oh, okay. One more condition is there. 0. Sorry. Okay. That is the condition. Now to study the integral in detail, we develop a fascinating inequality, namely the Chebychev's inequality. What does this say? So the Chebychev's inequality tells the following. Chebyshev inequality deals with the estimate of the set on which the function exceeds a particular lambda. Estimate of the measure of the set on which, so it deals with measure of E, measure of the subset of E on which exceeds So it's something like this, that we are looking at the measure of all those x belonging to E for which Now this is what we want to estimate, and we want to show that in fact it turns out that this is 1 upon lambda integral. So this can be related to the integral. Okay. So this is an upper estimate for this measure of this class. Right? Now we will look at this. I will make the statement soon, but see, it's something like this. See, this is R. I'm just giving a pictorial representation. Now we are now possibly working out functions which may take infinite values at some points and so on. So this is your f. I just put it this way. Okay. So that somewhere it is possibly taking the value. Now what we estimate is the following. So suppose this is a given lambda. So you look at the set on which this function exceeds this lambda. What is that? It is going to be, as far as whatever I have drawn here, it is this. So I can just call this E lambda. Now I am asking for the measure of E lambda. How does it compare with the integral of f? This is your f. Integral of f. Integral of f is essentially this area. Total area that you have. It may be finite or infinite in this case. We don't know. And there are two ways in which it could be infinite. That means it may take infinity as its value on a set of measure not equal to 0. On a non-zero, on a measurable set with a non-zero measure, it may take the value infinity. In that case, the integral could be infinite. The other situation is because the domain of the function is infinite, so that there will be contribution from there to the area. So both these are possible. Okay. For example, I'll give two examples. One, all the three scenarios. Take this function. This is fx equal to 1 upon and 0 over. So fx equal to 1, x not equal to 0 and equal to 0. Now on this, now you see the area enclosed, you know that from elementary calculus, you know that the area enclosed between this is infinite. It is infinite on two accounts. Okay. For example, suppose you were to consider the interval from minus a to where a is finite. Then of course E is so measure of E is So the measure of E is finite. However, this integral of f by mod x, fx dx is equal to this we know from elementary calculus. Okay. Now the second scenario is that you have a function something like this. So E is the whole interval minus infinity plus infinity. So this is the first scenario. Second scenario. So, right. Now you see that take the function to be the function fx equal to one by mod x for x belonging to minus infinity to minus 1 in 1 to and equal to say 1 x belonging to, so it's a continuous function, nice continuous function, but still you see that integral here the domain is an infinite domain, and it is in this case we know from elementary calculus so it can come by the function becoming unbounded on a set of positive measure, or the domain becoming infinite and at the same time the function not dying down sufficiently fast. Okay. On the other hand, suppose I modify this function. The third scenario is I take the function fx to be equal to 1 upon square for x not equal to 0 and equal to 0 or 1 or you want to whatever value you want to. Now in this case you see that we know that integral minus infinity to plus infinity sorry, I think I'll take this way, x belonging to minus infinity to 1 this 1 to infinity on this side, and this function I take as 1 x belonging to this is a continuous function. Once again it's of the form something that very sharply goes to 0 This is the function. Okay. Now you see that it's a continuous function, nice continuous function, but it's still defined on the infinite interval, and the function dies down very fast. The speed with which it dies down is fast. Therefore, you see that you get integral effects. It's fine. In this case, in spite of the fact that the domain is an infinite. So these are all various examples where the situations crop up. Now another example that we can look at is this. Fx equal to okay. So no, we'll look at this example later. Take it. And there are situations where you may get the function becoming unbounded, but still the integral will exist. I'll give an example. This example soon. Okay. So you can take the fourth example as chi of complements. Okay. So 1 by x square into chi of 2 complements. Now you can show that, so see, this function is infinite. On an infinite set, no. At 0, this function becomes infinite. Okay. But this function would become integrable. So you can show that this is integrable because x square dies down fast. So you can easily show that this is integrable. Okay. So what we need now is some estimate of the set on which the function exceeds a given value, and that is what is the content of the Chebyshev inequality, which relates it to the integral of f. Okay, so we'll write down the theorem. Non-negative measurable function and any lambda positive measure of such that is bounded by integral over f multiplied by 1 upon n. This is the Chebyshev. Now you see, this inequality gives lot of information. First of all, you see that you want to look at where the function becomes infinite. Now then this becomes this set. I mean, I'm just giving a crude explanation of the application of this. Then you see that that particular set is okay. Let us take a scenario. Suppose you have integral over EF is finite, but f infinite value takes the value infinity, at a set of points. Then you see that we have this estimate. For each lambda, this estimate is there. Now you see that the set x belonging to E fx equal to infinity is essentially the intersection of the set of all lambda. Now you can see that if this is finite, then for each lambda you have an estimate of this set. Okay, and as lambda tends to infinity, now you see that the limit of this. Okay, so limit what does it say? It says that the measure of x belonging to E fx it's on a set of measure 0, the function becomes infinite. Okay, or the set on which the function becomes infinite is this. In other words, it says that if this is not so, the set on which the function takes the value infinity is not a set of measure 0, then what happens? You see that the conclusion is that, you see, this would become unbounded with lambda, and this would become infinity, and therefore the consequence will be that integral of E over F is also infinite. Okay, right? Or you can write this as lambda times the measure of this is less than or equal to integral over E over F. And let lambda go to infinity. Okay. So we can come to that conclusion from this inequality. So there are very many ways in which you can possibly get some idea of the set on which the function becomes unbounded, and also about the measure of the set. If the function is a bounded function, then you can conclude that the measure of E has to be something like some such estimates are possible from this inequality. So let us prove this result. So we define that so that we take as lambda or lambda belonging to now suppose measure of E lambda then what happens? So let's see, to prove this we have to talk about the integral of this. Now the integral of this is defined as the supremum of the integrals of all those h which stay below this function f and have finite and is bounded, and also defined on sets of finite measure. So such h's are there. So we have to work through that. So for that, so this is the assumption that then what happens? Then you want to show that this inequality is valid. Let be now define E lambda n intersection so for each n belonging to n, this is a bounded set. Therefore, E lambda n bounded set. Okay. Now we define psi n to be equal to lambda times chi of lambda. So what you are having is this. The scenario is something like this. Something like this. Let's take some infinite values also. Now what you have is this. This is your lambda that you choose. This is E lambda. So this is E lambda. Suppose this function is like this, then this part is also in E lambda. So you have E lambda coming up as this set. So this is your E lambda. So whatever I mark with this yellow one is your E lambda. Now E lambda intersection minus n to plus n. See, so what you are doing is you are cutting it off with minus n plus n. So you are, in that case, you are considering only this much, which you know is a bounded measurable set. Okay, that is this one. And on that you define what? So what you do is we define the function to be psi n to be lambda times chi E lambda n. E lambda n, that is on this function, E lambda n is equal to 1 and then multiply it by lambda. So you are going to have this function approximated by this and this. Okay. So there are two things here. First of all, the function that you have is now defined as identically 0 to this, 0 over here, 0 over here, and 0 beyond this. Okay. And it is equal to lambda on this path, E lambda n. This is your E lambda n. On that you are taking the function to be equal to lambda. Elsewhere it is set as 0. Therefore, you see that psi n is bounded, measurable, that comes from the measurability of f, and with finite support. That is the outcome. So psi n is bounded, measurable with finite support. Further, these conditions are satisfied. Therefore, this is one of the legitimate class of functions which approximates the function f from below. Okay. Therefore, what you can possibly infer is that in the supremum, from the definition, of integral, it follows that integral okay, because this integral is defined as the supremum of all such integrals of all such functions. Therefore, whatever we think we symbolically represent is going to be the least upper bound of all these numbers. Therefore, this is satisfied. So, this is a symbol at the moment. Now, let us write down. So, note that psi n is bounded measurable with finite support and so this is the property that the function psi n possesses, and this inequality is a consequence. From the definition of this is true. Okay. Now let us start. Now what we have is obviously this. Now by the continuity of measure, infinity is equal to lambda times measure of E lambda. This we have assumed, this comes from that part, and this is essentially, here we are using the continuity limit n tending to infinity of measure of and that is lambda into integral over E psi n. And so what you have, this is equal to limit and that, because lambda we are keeping it fixed, and this is of course sorry, there won't be lambda here. Look at the definition. The definition of psi n is okay. Therefore, the lambda is absorbed this. Okay. Therefore, this is this, and that naturally is over and this is infinite because this goes to infinity. It's unbounded. Therefore, this is infinite. So you see that on both sides, you get infinity, and hence the inequality holds good in this case. Now we take up the other case. See, measure of that is a solution. And for this, let us do this in. So let define h to lambda that means on E lambda the function is defined as lambda, h is defined as lambda, and otherwise it is 0. Right. So what about h? Because its support is E lambda. So that's a finite machine. Okay. And therefore of the integral of we have this is what we want to estimate. This is equal to integral over E h, and this is less than or equal to. Therefore, which implies measure of E lambda is less than or equal to 1 upon lambda integral over E, so that the inequality forms. So this is a very nice estimate of the measure of the set on which the function f exceeds the value lambda. We shall see how we are going to make. Now, one of the conclusions that you can immediately make is that measure of E lambda can be made as small as it is by choosing lambda large. Okay. For instance, if integral over E f is equal to k, then all that you need to choose is lambda you choose as 1 by lambda less than k by lambda less than epsilon. Okay, right? So this estimate is there. Further, for a function, okay, for which finite, the set on which value infinity is summation 0. Now this is another conclusion. This arbitrarily small. Okay. So that is one conclusion. Now we can use this to get a further nice information about the function more deeper than what we stated. What we can possibly conclude is that if integral of f is 0, then f is 0 almost everywhere. That's the next thing. If and only if now this is a very so integral f equal to 0 implies f is 0 almost everywhere. How we will prove this result? First we assume this and then prove this. So we onward assume so what we want to conclude is that we prove that okay. So integral over E equal to 0 implies by Chebyshev's inequality. Measure of equal to 0 for every n okay. Therefore, what do we want to conclude? We want to look at this one. Now note that is equal to union and you know that each of this and this is equal to 0 is measurable. This is equal to 0. Okay. Because you get each of this or each of this. Which is 0. That is the reason. By Chebyshev. So this implies that is the first part. Now we want to prove the first. F equal to 0 almost everywhere on. Now let phi be a simple function and h a bounded measurable function of finite support for which so you can approximate it by h. So you can find a h like this, and then you can find a simple function having this satisfying this inequality. Okay. And okay. Zero. Integral phi equal to 0, which implies integral over E so we are using the fact that f is 0 almost everywhere to conclude that phi is equal to 0 almost everywhere. Okay? And if phi is a simple function which is 0 almost everywhere, then you know its integral. Integral over E of phi is equal to 0, which implies integral over E h is 0 because phi is less than or equal to h, and h is approximated through such phi's. So these are all zeros. So phi is an arbitrary simple function that you have chosen with this property. Therefore, this is 0. And again, you are approximating f by such h's. And this is 0 for every h means this is. Okay. So that concludes. So this completes it. So this Chebyshev inequality is something very useful to draw conclusions about the behavior of the nature of the function. Okay, I think I will stop here. Thank you very much.